Hello students, welcome back. And we are continuing our discussion on the thermodynamics of open systems, and we are looking at the properties of chemical potential. We have already seen that if I have a composite system with two compartments A and B, then under the condition of constant temperature and pressure, if there is a common component between A and B, and if I allow this component to be transferred between these two components, then the spontaneous transfer of matter occurs where the chemical potential mu I of this component is from a region of high value to a low value, and when equilibrium has been achieved with respect to matter flow, then mu I value will be the same all throughout this composite system, irrespective of whether I'm looking at the compartment A or the compartment B. Now with this, let us now try and understand the difference between chemical potential and something like the concentration of the system as given in terms of the number of moles. Now, you would obviously wonder, while the other two intensive variables are very easily measured, can we very easily measure the chemical potential? The answer is no, and that is the reason why we would like to connect the chemical potential to the more commonly encountered and commonly measured quantity of the system, that is the composition or the concentration. And usually for a mixture of substances, we express the composition of the system in terms of number of moles. Now when I have an open system, the number of moles are undergoing a change in value when I am inducing a change in state. So now we are going to look at how I can connect the chemical potential to the change in composition of the system in terms of temperature and pressure. So my assumption for this case would be, let me change the composition of each component by the same extent. So if I have the ith component with composition Ni, in that case, I will introduce dNi as Ni into dN. And therefore, I can write down that as a consequence dGTP, which from this expression will now have no contribution from this term and no contribution from this term, but only this term. This would be given by mu I Ni into dN. Now, so what is dN? I understand that for a finite change, I would have each type of component undergoing, say, about 10% change in its composition. So in a finite process, instead of dN, I will be talking about delta N, and I'm saying that, well, let me say that delta N is 0.1. Therefore, if N1 is equal to, say, 5 moles, then what would be the new value of N1 as the system undergoes a change in state? The new value is going to be 5 into N1. The new value of N1 is going to be N1 plus delta N, and that is going to be, so all I'm saying is N1 is going to change by 0.1 or 10%. So N1 is now going to be 5.5 moles in the new state. If I have N2 equal to 1 mole, then in the new state N2 prime is going to be 1.1. That is because each type is undergoing a change by the same extent. So this is what I mean for an infinitesimal change in the composition of each type, dNi is equal to Ni into dN. And therefore, at a constant temperature and pressure, I can replace Ni here and write it like this. But obviously, dN doesn't depend on which type of component you are looking at, and therefore I can take it out and write it outside this bracket. And therefore, I would be able to say that, well, I know that dGTP is G into dN, as D is extensive. Now, if I compare these two equations, what is going to be my immediate conclusion? My immediate conclusion is going to be that G, that the Gibbs free energy at a given temperature and pressure, is nothing but a summation of mu I dNi. So this expression is based on a perfectly general construction and exploits the property of G as an extensive quantity. So now, at a given temperature and pressure, let me have a look at this particular equation again. We have already shown that mu is a function of temperature and pressure. And here I have the composition of the system expressed in terms of Ni's. Therefore, obviously, I can say that the Gibbs free energy that I have written on the left-hand side is indeed a function of temperature, pressure, and the composition of the system. Now, let me take a differential of this equation under the condition of given temperature and pressure. Now, this I can write as summation over I going from 1 to m. Then this would be mu I dNi plus Ni d mu I. That is correct. But what is it that I already know about this system? I already know that from the thermodynamic equation of state for an open system, dGTP is equal to mu I dNi by definition. If I now compare this expression to this expression, what would be my immediate conclusion? My immediate conclusion would be that Ni d mu I, when summed over all I values, that must be equal to 0. And these three equations together give us the different forms in which you connect the composition of the system to the chemical potential. And these are collectively known as the Gibbs-Duhem relation. What we are going to do next is we are going to apply the Gibbs-Duhem relation to understand the thermodynamics of a mixture of ideal gases. Now, what I have here is a situation where I had the ideal gas A and I had the ideal gas B. So, in the initial equilibrium state, I had Na moles of the ideal gas A maintained at a temperature T and P, separate from the ideal gas B, which was also maintained at a given temperature T and P, but it has Nb moles of it. Now I allow these two gases to mix such that in the final equilibrium I have the same temperature T, then the partial pressure of the gas A is Pa, the partial pressure of the gas B is Pb, such that in the final mixture Pa plus Pb is equal to P, that is the same pressure at which the pure substances A and B were present before mixing. Now, we are going to look at the application of Gibbs-Duhem relation for this mixing process. Now, before mixing, therefore, I would like to emphasize that all the components are in their respective pure phases at the same temperature and pressure. Therefore, for the ideal gas A in its pure phase, I could write down that mu A star is equal to mu A naught at the temperature T plus RT ln P by P naught. Similarly, I could have written that for B in its pure phase, mu B star would be equal to mu B naught at temperature T plus RT ln P by P naught. Therefore, before mixing, what would be the Gibbs free energy of each of the pure phases taken together but not interacting with each other? So before mixing, G initial is going to be Ni into mu I star, where I goes from 1 to m. So in this particular example, m is equal to 2. So G initial in this particular case is given by Na mu A star plus Nb mu B star. And if I use these two expressions, I know what G initial is. Now let us now move over and use these results further. After mixing, if the temperature of the mixture is T and the pressure is P such that P is equal to Pa plus Pb, then I can very easily write down that the final Gibbs free energy is going to be Ni mu I. How could I write that? I could write it by using the Gibbs-Duhem relation. Now when I do this, for this particular example, I can simply write that G final is equal to Na plus mu A plus Nb plus mu B. If that is so, then the question is, what is mu A and mu B? Please remember, now after mixing, both the components are now present inside the mixture, and I know how to write down each of these quantities in the mixture provided I know their partial pressures. Therefore, I am going to replace mu A by this expression, which we have already derived for an ideal gas. Similarly, for mu B, I am going to replace it by this expression where I have, instead of mu B naught at temperature T plus RT ln partial pressure of B divided by P naught. Now what you find here is that I have a generic expression for G final where I have Na multiplied by some quantity plus Nb into multiplied by mu B naught plus xbp by P naught, and therefore G final can be very easily shown to be equal to G initial plus nRT into a term which is xa ln xa plus xb ln xb. Therefore, in general, I can write that delta G mixing, which is G final minus G initial, that is equal to nRT xa ln xa plus xb ln xb. So what is small n here? Small n is nothing but Na plus Nb, the total number of moles of the two ideal gases present in the system. Now, therefore, by the application of Gibbs-Duhem relation, what we have found is as follows. We could identify the initial value of the Gibbs free energy before mixing at a given temperature T and pressure. And this is given in terms of Ni and mu I star, where mu I star is the chemical potential of the ith component in its pure phase at the temperature T and pressure P. Now, after mixing, if I know the partial pressures of the individual components in the mixture, then I can evaluate G final, because G final depends on mu I, and mu I for the ith component now depends on the partial pressure of the ith component in the mixture. And therefore, I find that delta G mixing can be expressed in terms of the composition of the mixture using these relationships. Now, how did I introduce the composition of the mixture? All I did was I used the Dalton's law for a mixture of ideal gases, where each Pi is now expressed in terms of the mole fraction Xi of the ith component and the total pressure P at which the mixture is being maintained. Now, this particular expression, as you see here, is a usable expression for any given mixture of the ideal gas, provided you know the total number of moles and the mole fraction of each individual component in the ideal gas mixture. Now, moving ahead, then what happens if I plot the mole fraction of the component A in the binary mixture of A and B along the x-axis, and I plot delta G mixing along the y-axis? What will happen? I will get an expression, a plot like this. Now, what is happening here? When I start from Xa equal to 0, what do I have? I have the pure substance B. Therefore, the corresponding value of delta G mixing is equal to 0 because there is no mixing at all. When I have Xa equal to 1, there is no question of mixing again, and I have the pure substance A, and which is delta G mixing equal to 0 again. Now, what happens in between? I can vary the mole fraction of A from a value of 0 to 1, whereby I can have the, when mole fraction of A is 0, it is the pure phase B, then I go on increasing the relative proportion of A, so that it goes from having a very low mole fraction to a very high mole fraction as is given here. Now consider the situation where Xi is a very small number. In that case, what I will find is as follows. Xi is less than 1, and therefore I will have the delta G mixing given by nRT into Xa ln Xa plus Xb ln Xb. Now, for any given composition of this mixture, Xa, Xb, both of them are less than 1, because Xa plus Xb by definition is equal to 1. If that is so, therefore, I can say ln Xa or ln Xb must be less than 0. If that is so, in that case, I have two negative terms combining to give me delta G mixing, and therefore delta G mixing is going to be less than 0 for all values of XA and XB less than 1. So that is exactly what has been shown here. So obviously now you do expect that there will be a negative value of delta G mixing irrespective of which composition of the mixture I am at, provided XA and XB, none of them is equal to 0. Now let us also consider the following. What would be the nature of the plot delta G mixing as a function of XA? As you have seen here, you do see an extremum. Why is that so? That is because as you go on increasing the mole fraction of XA, the mole fraction of XB decreases on this side, and therefore delta G mixing, which has contribution from both XA and XB, would be expected to show an extremum, which in this case will be a minimum. Therefore, if you take a derivative of delta G mixing with respect to Xi, or in this case XA, you should be able to show that this minimum would appear when XA is equal to 0.5. And let me remind you that this is the situation that we do have when I evaluate the change in entropy of mixing as I go on changing the value of XA. And you would see once again here, upon mixing, there is no change in internal energy. This is because you are mixing ideal gases. Therefore, you can find out the change in entropy of S during mixing as delta mixing of S. And if that is so, you will be able to see that if I divide the right hand side of this expression by T, I would get the delta S mixing. And once again, and I'll have to take into account a negative sign, because in this case delta G mixing is equal to delta H mixing minus T into delta S mixing. Therefore, now delta S mixing is given by minus of NR summation over I Xi ln Xi. And here, as I see, because of the fact that delta G mixing by NR T looks like this, delta S mixing by NR will now show an exactly opposite behavior. And here, instead of a minimum as shown here, you are going to get a maximum at Xi, XA in this case, equal to 0.5. So now we have seen this example where I have a spontaneous mixing of an ideal gas. The other instances which employ the fundamental concepts that have developed here that involve changes in composition are phase equilibrium and chemical reaction equilibrium. Now, how are these things different from the mixing of ideal gases? While we were mixing the ideal gases, then we had two implicit assumptions. The first one being, my system is stable under the given condition of temperature and pressure while I am mixing the different components. But it may not be so. And even if you have a pure substance, at a given temperature and pressure, the system may be stable in more than one phases. and therefore comes the concept of phase equilibrium. If you change the temperature and pressure, in that case, the matter can flow from one phase to the other depending on the chemical potential value of each phase. And an equilibrium is achieved between the different phases when the chemical potential is the same in different phases of that pure substance. And therefore, phase equilibrium talks about matter flow from one phase to the other and the eventual establishment of equilibrium with respect to matter flow between coexisting phases at a given temperature and pressure. While considering the ideal gas mixture, we also assume that these gases cannot undergo any chemical reaction between them. So in that case, I can remove that assumption and think of a chemical reaction equilibrium whereby I have more than one components present, and during the progress of the chemical reaction, the number of particles, the number of molecules of each type of component can change. And therefore, the beginning of the reaction, the initial equilibrium state, and the final chemical reaction equilibrium may be considered to be a transfer of matter from one type of a component to the other as a result of chemical reaction. And therefore, the same set of considerations apply to both phase equilibrium and chemical reaction equilibrium. And this is what we are going to take up in my next lecture when I discuss how to use the concept of chemical equilibrium in the study of equilibrium between two coexisting phases. Thank you.